But I'm going to move to our next speaker, who is Colette Schissel. Colette is a PhD student in chemical engineering here at the University of Texas, and she's been working extensively on issues related to quantifying uncertainty. How do we quantify uncertainties in these various measurements that we have? So Colette, let me hand this over to you.
My name is Colette, and I am a PhD candidate working with Dr. Allen at UT Austin, and I've also worked with the Oil and Gas Methane Partnership as part of the United Nations Environment Program. And so today I'll be talking about some case studies in OGMP 2.0, Level 4 and Level 5 emissions reconciliation. So I'll first start off just by introducing OGMP 2.0. It's a United Nations framework for voluntary global and measurement-informed methane emissions reporting for the oil and gas industry. And part of OGMP 2.0 is this gold standard of reporting, and that's awarded to companies who are reporting all of their material assets at a Level 4 inventory with demonstrated effort to move towards Level 5. And so I'll just define then these Level 4 and Level 5 inventories. A Level 4 inventory is defined as emissions that are reported by source type using specific emissions and activities factors that are either based on direct measurements or asset-specific equipment information and detailed engineering calculations. And a Level 5 inventory is then on top of that Level 4 inventory, conducting some amount of site-level measurements and reconciling these site-level measurements with your source-level inventory. And so I'll make a quick distinction between what source and site-level measurements mean. Just kind of for clarity, a source-level measurement is something that you can attribute the equipment type to where the emission is coming from. And then a site level might capture a collection of sources at the site, or it might capture different sources across different sites in an aggregate measurement. And so this reconciliation process it can be pretty tricky. The way it's defined in the technical guidance documentation is that reconciliation is the process of comparing this source level or Level 4 inventory with independent site level measurements. And that's kind of a difficult task. And the reason behind this difficulty is that, as we've kind of talked about throughout this meeting, is that methane emissions themselves are inherently variable. We have a lot of skewed emissions and a lot of intermittency in these emission events. And then measurement technologies themselves can span a wide spatiotemporal range. So you may have something like a satellite measurement, which has a coarser spatial resolution and potentially a high detection threshold. And you might have measurement technologies all the way down to the source level or a continuous sensor that's providing kind of specific information, but at a much smaller scale and at a much finer temporal resolution. And so the implications of all of this variability, both across measurement technologies and the emissions themselves, is that these emission estimates are never going to agree exactly. You're never going to have a source level estimate that exactly matches with a site level measurement. And so in the process of reconciling it and effectively comparing these different types of measurements, what reconciliation really means is understanding why these emission estimates are different and trying to learn something as you move closer to comparing source level and site level measurements. And so there's a number of reasons why these estimates might be different. The first is similarly about this variability. It could be that these measurements were taken at different points in time or across different sample populations, and you're just capturing a different point in that time series, and that's why it's higher than you might expect or lower than you might expect. It could be that certain sources are being over or underestimated depending on your source level methodology, or it could be that sources are missing from your Level 4 inventory altogether. And these kind of boil down to two different questions. So the main idea here is that we need to understand measurement and measurement-informed inventory uncertainty in order to understand errors in source level quantification. So we need to know what the error or uncertainty is in our sample populations and in our measurements themselves, and to be able to quantify that uncertainty, to contextualize measurements, to really get at the root of, is there an issue in the way that I'm quantifying my Level 4 inventory, or are these site level measurements and this difference kind of a product of maybe just needing to expand my sampling population. So I'll dive a little bit deeper then about this uncertainty. There's 3 different types of uncertainty that we like to think about. The first is measurement uncertainty. So this is the uncertainty that's associated with the primary measurement technique. So for example, it could be the error that's introduced directly from a receiver, or some uncertainty in reading that primary form of measurement. And then that primary form of measurement gets converted to an emission rate, and that introduces a secondary form of uncertainty. And this step typically involves dispersion modeling, and you might introduce meteorological data, and that itself has uncertainty. And so there's kind of this second level of uncertainty that's introduced. And then finally, when we take these measurements, we have to convert them to different scales of time and space. And so there's extrapolation uncertainty that we then introduce, which really kind of gets at the heart of this reconciliation. So we might take a limited number of measurements in time or space, and then assume that that's representative of our emissions for an entire year. And there's some uncertainty in making that assumption. And so I'll kind of dive into this extrapolation uncertainty a little bit more and talk about some methods and metrics for quantifying these types of uncertainty. So there's 2 different types of extrapolation uncertainty, just to be kind of explicit. The first is temporal extrapolation. So this is taking measurements with a limited amount of temporal coverage and scaling that up to a larger time scale. So perhaps taking quarterly aerial measurements and then assuming that that is representative of your emissions, your mean emissions for a year. And then there's also spatial extrapolations. This is the extrapolation involved with taking a limited number of measurements at a certain source or across certain sites and assuming that that is representative of your entire region. And so as we kind of start to think about how to reconcile source and site level measurements, we need to take enough measurements such that the mean of these sampling populations is as close as we can get to the true mean of the full population. And so the main question that comes from this is then, how frequently do we need to sample and how many sites do we need to sample to minimize the uncertainty that comes from this extrapolation. And I'm going to look at 2 different case studies to try to begin to answer these questions, or at least provide some next steps to consider as we think about designing measurement campaigns. So I'll first look at the Barnett Shale in Texas to understand this temporal extrapolation uncertainty, and then I'll look at a case study of the Green River Basin in Wyoming to talk about spatial extrapolation uncertainty. And I'll go kind of quickly through the technical details, and there's more information out in the posters, but the first step for both of these case studies was to simulate these emissions. And so these emissions were simulated using detailed source level data, kind of depending on what the best available data was. And these emissions were simulated at fine spatiotemporal resolution, so the emission data was tied to a timestamp and a geographical location. And so in the Green River Basin, I simulated about 50 representative sites for 1 year, and I added in this skewed behavior where we see high emitting events that occur 1% of the time. And the durations of these events varied from shorter duration to longer duration to see how that impacted the results. And then in the Green River Basin, I simulated upwards of 1,300 sites over a 10-day period. And then the next step was kind of sampling or mimicking what these sampling campaigns might look like. So for the Barnett Shale, I sampled these time series on the frequency of weekly to annually. And for the Green River Basin, or this spatial extrapolation case study, the time series were sampled in sample populations of 13 sites, or about 1% of the total population, to 650 sites, or half of the full population. And then finally, these sampled observations were extrapolated to compute an annual inventory estimate, and then the error in that estimate was compared to the sum of the true emissions. And so for the temporal extrapolation, it was a simple approach. The sampled measurements were averaged together, and then that average emission rate was assumed to be the average across the entire year, and that was scaled up to an annual rate. And then for the spatial extrapolation, we looked at 2 different types of extrapolation. The first was a simple linear approach where we scaled it purely just based on the number of sites in our sample population. So if there were 10 sites in the sample population and 100 in the full population. We just multiplied all of the emissions by 10. And then the second approach is a little bit more involved, and we looked at source-based extrapolation. So we looked specifically per source type, how many sources were considered in the sample population, and then extrapolated those emissions to the full population. And these were kind of the preliminary results. So we have the average absolute percent error as a function of measurements per year and the number of sites. And the different extrapolation methods are shown in green and blue. And you can see kind of at first glance that there's a lot of variability in these results. So for the temporal extrapolation case study, quarterly sampling on average can potentially lead to around 50% error, or it can be less than 10% error depending on the duration of these events. And similarly for the Green River Basin, between around the 65 site sample population, which is about 5% of total sites, which might be something that's realistic for an operator to measure. We saw a lot of variability where some estimates were really good and some had close to 100% absolute error. And so our kind of first pass of results show that extrapolation error can be quantified, and it can be a metric for determining data quality or determining uncertainty of a measurement campaign, but results can vary significantly. And so it's kind of unclear looking at these preliminary results how to consistently determine if a measurement campaign is capturing a sufficiently large number of measurements. And so we took a closer look at what's happening at the source level. And so for the temporal extrapolation case study, we looked at the duration of these high-emitting events. And for the Green River Basin, we looked at the skewness of the emission sources themselves. And we saw more data trends start to emerge. So for the Barnett Shale case study, it's highlighted in yellow here, but if the duration of the event was longer than the time in between sampling, we saw a pretty steep decline in the error that we observed, and then that error kind of leveled off, and you weren't really going to get a much more reduction by increasing measurements. So if this duration ratio was greater than 1, we saw kind of a rapid decline in the average observed error. And kind of similarly with the Green River Basin, we defined this capture ratio, which is a little bit more technical, but essentially it kind of serves as a proxy for how well you're representing each source in your sample population, weighted by how skewed the emissions from that source are based on your source level measurements. And so when you plot the average error as a function of the capture ratio, you see all of the data from these two graphs can collapse onto a single plot. And you see a similar trend emerge where you have a pretty rapid reduction in error up until you have a capture ratio of about 0.2, 0.3, and then it kind of levels off despite increasing sample size. And so the main takeaways from this initial case study is that the site level measurement variability will depend on source level characteristics. So the uncertainty that you're introducing in different measurement campaigns will depend on what's happening at the source level, whether you have highly intermittent events or highly skewed distributions of emissions. And so source level characteristics can directly inform site level measurement campaigns, and they can be used to quantify extrapolation uncertainty. They can be used then to minimize that uncertainty, and they can be potentially used to inform the selection of sites that you're going to measure so that you can reduce your uncertainty while also minimizing the number of measurements that need to be taken. And then just to kind of tie this all back to what it means in the context of reconciling emissions estimates across scales, as we minimize extrapolation uncertainty, or at least start to understand how to quantify it, we can make an informed approach towards reconciliation, and it can help contextualize different measurements to understand what they mean in the context of one another. And that can be used as an indicator to understand whether this variability between measurements is due to variability across space and time scales, or whether it's an indication that there might be some error in the way that we're quantifying different sources or the way that we're constructing our source level inventory. So thank you to everyone that helped make this work possible, and I think that's all I have then. Thank you.
Thanks, Colette. And I have one question for you from the audience, and it's a tough one. Okay. You did your work in model world where you have simulations and you can somewhat artificially separate temporal uncertainty and extrapolation from spatial. Any thoughts on how those two combine? So you're out in the real world now and you have both spatial uncertainties and temporal uncertainties simultaneously coming together. Any thoughts on that?
Yeah, I think it will kind of make these true measurements that we make, more uncertain because you will have both types of uncertainty coming into play. And I think it can also be potentially leveraged if you understand how much uncertainty reduction you'll get by sampling in time and how much uncertainty reduction you'll get by sampling in space. You can potentially optimize your measurement campaigns to either include a larger sample population or maybe include more time measurements if you know where the bulk of your uncertainty is coming from.